Okay, lecture number 9. Today we will cover memory technologies. You might think we have already talked about memories, right? Like when we had the external bus interface. There we were really looking at bus interfaces. This time we will actually looking at memory technology. So what's inside of these memories and how do they work internally? Before we start though, homework number 2 I have posted. It's a written homework this time, so you have to actually print it out and hand it in paper. Crazy, huh? Next week, so it's due in 1 week from now, on Tuesday the 19th. In class, please bring it in here. Make sure, a couple of tips here, make sure that your encoding functions are as small as possible. So if there will be some translation that you have to do from assembly into opcodes and from opcodes into assembly. So make sure that if you go from assembly into opcodes that you choose the smallest encoding possible. So if there's a possibility to make it in 16 bits, making it a 16-bit opcode, not a 32 one. Sometimes you also have to think a little bit about stuff, so you will see what this is all about when you look at the homework itself. Graduate students, a reminder, February 21st is the deadline for your platform proposals for your presentations. Please talk to me before the 21st, okay? So that if I say no, you have time to actually look and search for something else. All right. Minute quiz. But before then, homework 1.4, like assembling the PCBs. Who has it assembled and whose LEDs started blinking? Only 3? All the others are broken? Not done yet? Try to get this done and over with if you haven't done it so yet. All right? Yes?
On the launch pad, which pin is 1 when you're programming?
I don't know. I would have to look at it.
I don't know which way from my board.
Doesn't it have labels? Do you know?
I follow your dad exactly, right? Just put the board upside down.
Yeah, a lot of people say that.
Okay.
What you did then.
The problem is if you don't put it on right, then you hook up power to ground, and that could be a potential problem. Look at the Launchpad's schematics. I'm sure there is like a mark for pin number 1 on the Launchpad, and then you can tell which one is what. And then you need to make sure that your pin is this way or the other way around. Yeah. Sorry, I don't have a better answer. Okay, minute quiz. Let's do head is minute quiz, tail is no minute quiz. And it's head. Whoops. Everybody ready? Okay, 1 minute sharp. Thirty seconds. 15. 5. And that will be it. Okay, what's the answer?
10 to the 13.
Sorry? 10 to the 13. That's a huge number.
Is that just the 1 meg plus hertz?
Yeah. It's 1 megahertz plus 10 hertz, right? ppm is parts per million. So if nominal frequency is 1 megahertz, then if you're 10 ppm off, you're at 1,010,000. Right? Sorry? I will write it down. 1 second. Oh no, wait, I killed that one. So if F0 is 1 megahertz, right? 10 ppm of that is 10. No units, right? So then our frequency will be at 1, 2, 3, 0, 1 megahertz. Yes?
I think I read your question wrong. Yes.
Okay.
But I got the dates right.
Good. That's good. That's important. It's just a little mini quiz, so it doesn't count much. All right. I actually noticed last time that I forgot a whole part of the lecture. And I already did part that I was supposed to do in this lecture. So let me backtrack a little bit. We were at this stage here, right? We talked about resonating elements a lot. We talked about clocks a lot. And then we talked about how to distribute clock signals inside our microcontrollers, like using these big muxes and all the clocking system that's in your Smart Fusion. The thing that I kind of just brushed over was this part. I talked a little bit about software, but I didn't really talk much about hardware counters and how they really work in detail. So what I want to do quickly now is actually go into the blackboard and do a couple of exercises and actually design with you a timer to see how a timer could work and how they actually work. Okay. So from last lecture, what do you remember about the timer? What is the key element that you have in a timer? What? An oscillator, yes, but then what else is there? A counter, right? So you have a counting register that has an input signal into a clock input, right? And this is your clock. This comes from the resonating element with its driver and whatever is out there, goes into a counter that counts. Always 1 if there is a rising edge, usually. Now, you can usually configure this counter sometimes to count up or count down. Most of the time it's an up counter because you're interested in time going up, but sometimes you also want to count down. And other times you can actually configure them in mode where they count up and down. So they count all the way up to its highest number, and then they count down again from that higher number to 0 instead of overflowing. So there's a lot of different ideas that you can do. What's the most important thing about your counter, though? Yes. It usually has a certain number of bits, right? N bits. For example, in your Smart Fusion, you have a 32-bit counter that you can link up with a second one to make a 64-bit counter if you want to. So how does that work? How can you take two counters that are 32-bit and make them into a 64-bit counter? What do you need? Yes?
Just a connection from the last bit of the first to the first bit of the second.
Basically an overflow signal, right? So there's a signal that pretty much every timer gives you when it overflows, when it goes from its highest number, so 2 to the power of n minus 1, back to 0. That's what's called an overflow. And what they do in the Smart Fusion is they take that overflow signal and basically hook it up as the clock input of your next counter. So the next counter just counts how often this counter overflowed and technically thus doubles your bit length. Right? Okay. Now last time, if you remember, we had two different functionalities that a timer usually offers. Do you remember what this was? Sorry? Set and reset, yes. That's more a software interface. But yeah? Yes, capture and compare. So what is the capture? What is a compare? Let's first do the capture, because that one is slightly more intuitive. So a capture is another register that sits up here that has a wide bus interface into this timer. And what happens is that when there is a signal from the external side coming in, when this signal comes in and has a rising edge, or you can configure it to sometimes be a falling edge, let's take it a rising edge. When this signal rises, it will take the value that's stored in here and copy it over into your capture register. Right? So now it's saved. So this counter will keep incrementing as that one clocks in, but it will save the value in here that was written in your counter when this signal came. Okay? Who has done digital logic stuff? Almost everybody, right? I think that was a prerequisite if I'm not mistaken. What can be dangerous about this? They could be out of sync, right? If by mischance this clock here comes in, well, this counter here is still incrementing, right? If you remember, if you ever designed a counter is not instantaneous. If you looked at the model sim system of your counter, you see that the bits change at different intervals of time. So if this thing here comes in while this is just incrementing, then your capture value will be garbage, right? So oftentimes your captures have actually logic in them to synchronize to this clock up here. So what we will do is there will be some logic in here that will make sure that you capture an actual value, not while it actually is incrementing. Oftentimes it's called a synchronization block, and there are lots of different techniques of dealing with this meta instability that it does not happen. Any questions to that? Okay. What's the problem with these things then? Assume you have a block here that makes sure that this will never be meta-stable. What could be the problem? Multiple samples? Not really, no. Yeah?
So when you, sorry, back to, I could have asked the question earlier, but when you said that it could be transitioning right when you capture a new value, or
yes.
New value will be stored in your capture register, or your clock will just count over your new value?
No, what will happen is that this value here will be something in between while it was incrementing. Right. So incrementing doesn't mean that what is on here is just one too low or one too high, right? Because the increment is actually flipping a lot of different bits occasionally for incrementing just by one. So if you capture it in that instability, you will actually capture garbage in here. That will just be this value at that instant in time where this was still flipping around.
You're saying the capture will capture...
The capture will capture what's in here right at this time. And that does not mean that it was the one before or the one after. But you can deal with that with logic that comes in front, making sure that the capture can only capture this value when it is stable, right? But there's a problem with this logic. what can happen is that sometimes it can add a delay into your captures. So that, assume this happened at the time when this was metastable, but then your block delays it until you are in +1. Or sometimes they have to actually do it already a lot before this one here starts incrementing, just to make sure that you don't hit that particular time. So it can be that your capture is actually +1 or +2 later than the actual signal came in. How to figure out what happens is you have to go and read the documentation of your timer units to make sure that what you actually have there is understood in your software and you can take care of it. Oftentimes it doesn't really matter that much, but sometimes if you really want to have this specific time of something, these kind of things can be very important. Questions to the capture? Yes?
If we invert the capture signal,
Invert?
invert this signal, so for example, it's falling edge capture.
Yeah. That's possible, oftentimes, yes.
And
Oftentimes you can configure, there's another block here that you can configure and say this is sensitive to a falling edge, sensitive to a rising edge, sensitive to both edges. So there's lots of different configurations. And it oftentimes depends on the manufacturer and the person that made that particular peripheral. Yes?
Well, I think what he's asking is, say the timer gets updated on a rising edge of the main clock, and then the capture compare register gets updated on the falling edge of the clock.
That could
so it's so that'll, I don't know how long the propagation delay is on the timer.
Hopefully it's less than half a
Yeah,
clock.
hopefully. But I mean, and then the capture compare register is just like a D flip-flop where you tell it to sample and then but it won't happen until the next clock. Yes. Okay. So that might fix it.
That might fix it. Yes. That's probably oftentimes how they implement the synchronization bits. Okay. So now what can you do with such a capture? What could this be used for? Yeah?
Doesn't our computer have like a current time since current number of milliseconds? Like
Unix time?
70? Yeah, exactly. Right. I mean, isn't that one of the uses?
Similar, yeah. But there, you don't have really a capture. All you do is you go and read a counter, basically. In a computer, it's actually the Unix time is implemented differently. It's probably not a specific hardware counter in that particular case. But yes, you could start counting from a certain specific time point, but then you don't use the capture. What do you use a capture for?
UART auto bitrate detection.
UART auto bitrate detection. Okay, that comes later on. Yes, so you can detect a certain signal, right? Like you can use this now to measure time of a certain event, or more specifically, you can measure the time between two different events, right? Assume you have a wheel that turns, and every time it comes back to the top, it will give you a signal like this, right? So now, using your counter, you capture twice the time it took. So the first time when you're at the top, and then again when you're at the top. So now you have 2 times. You subtract one from the other, and then you know how many counter clock ticks you had between the wheel going once around, right? So now you have counting clock ticks. Let's say you had 257 ticks. How can you now relate that back to time, to actual physical time? You use your clock frequency, exactly. That way you can now figure out how long it took in real time for the wheel to spin around. So that's what captures are used for, okay? The second thing was a compare. What's a compare? Well, it's just yet another register. That's in here. And this time, instead of being filled from your counter, you fill this register with the time, right? And then what the hardware does is it compares the value in here with the value of your counter, and once they match, it will do something on the output. For example, what it could do is it could interrupt you and generate an interrupt, or oftentimes they're linked up to a GPIO, and then There's a lot of different options that you can do, but oftentimes what it will do is it will toggle a GPIO pin. So when it was 1, it will set it to 0. When it was 0, it will set it to 1. Whenever this and this matches. And there are lots of different options there. Sometimes you can have a set only, sometimes you have a reset only, or a set reset, reset set, etc., etc. Yet again, can be a very complicated thing, but the principle of a compare is always the same. It's a value that you write in software into that register, and whenever that register matches with a counter, something will happen. An action will be taken. So what could you use a compare for? Loop counters? Yes? Pulse width modulation? Scheduling an event, exactly, right? Scheduling an event, it would generate an interrupt your software, and you can do something at that particular time. PWMs are very important utilities. Oftentimes there, you actually use 2 compare registers. So everybody know what the PWM signal is? Yes? Right? PWMs are defined by a period and then a percentage in between. So we have a signal that's low and comes high for a certain amount of time and then keeps going. So we have a period here, P, and you have a width. Let's call it W in our case. So you need basically 2 compares saying that one of them will be the period of your signal, the other one will be the duty cycle of your PWM signal. So oftentimes what happens is that you have one compare that when this guy here reaches the first compare, it will go back to 0. Instead of having to overflow, it will always count to what this compare is set to. That will give you your period. And then you have a second compare, which will be in between 0 and what this value is, which will give you that duty cycle. And then whenever the counter reaches that second compare, it will toggle a bit too high. Did that make sense? So, for example, in the MSP430, what you will have is the period will be the register CCR0, and the width will be CCR1, right? So assuming we have a 32 kilohertz clock, so clock is 32.68 kilohertz. How could we generate a duty cycle? No, how can we generate a period of half a second with a duty cycle, let's do, of 80%? Okay, so let's say period is 2 hertz and W 80%. Get together in teams of 2, solve this quickly. I want 2 numbers. What would you write into CCR0 for the period? And what would you write in CCR1 for the duty cycle? It's 2 numbers. Clock is 32.768 kilohertz. The clock is your speed of your counter. So every clock tick your counter will increment by 1. So we need to show the So how many clock ticks do you have to take to get to 2 hertz? Sorry?
About 16K.
16K? Yes? What is it exactly?
16.384.
So it's 2 to 14, right? you notice this is 2 to the 15, right? So to get to 2 hertz, it's just 2 to the 14 counts. Will be half of this one here. So you have 32.768 clock ticks per second. So you have, when your counter reaches to the 14, half of it, you will be at your period. Yes?
So the frequency is 2 hertz, and the period is
That's a period.
a half a second.
It's half a second, yes. Yeah.
I was confused because the period equals 2. That would be 2 seconds.
I'm sorry, no. The period will be 2 hertz. So that's half a second. So every, okay, yes, I'm sorry.
Period is in seconds. Hertz is in 1 over seconds.
Better? Okay. So what you do is you write into your CCR0 2 to the 14 so that your counter will start at 0, count up to 2 to the 14, and then keep counting at 0 again. Right? So it will do something like this. This is time. This is count. It will count up to the value stored in CCR0. And then it will go down and start again. Go down, start again. Okay? While the time from here to here is 0.5 seconds. Sorry, this is a little tiny. Running out of space. Okay? So now how can you generate a signal that has 80% as its duty cycle? Sorry?
Just take whatever is 80% of what's in CCR0. So
Correct. So 0.8 times 2 to the 14. Can somebody calculate that?
13,107.2.
13,100?
7.
Oh, 7.2. Oops. That's a problem. Right? What do we do with this 0.2? Round it, yes. So we are not exactly at 80%, but we are really close by. Right? So if you write this now in CCR1, what will happen is when the count reaches that particular value, here, it will flip the GPIO. When it reaches this one here and resets, it will set it back to 0. It will keep counting back up to 80%. It will flip it again, high, gets low again, gets high again, gets low again. And now it's really easy to change your duty cycle on this particular signal because all you do is you rewrite this particular register to a new number, and that way you can change the duty cycle from 0 to 100%, depending on what you need. Any questions? No? Yes?
Your CCR1 is flipping the bit, right?
Yes, so CCR1 would flip the bit from 0 to 1, and then when you hit CCR0, it would flip it from 1 to 0. And how this all is implemented in the timers always depends on your manufacturer. So this is CCR1 and CCR0 is actually from the nomenclature that the MSP430's timers use. The Smart Fusion's timers cannot generate PWM signals because there's no GPIO signal or GPIO unit that's connected to them. So they can't flip external pins actually. They have PWM units themselves directly, which work very similar. And I think, if I'm not mistaken, in Lab 5 you actually will implement your own PWM. Like you implement your own timer and have to flip a bit accordingly to what you do in it to generate a PWM signal. Any questions? Okay. Then let's go to the next topic. So right now, assume you have 5 compare registers. The compare register, as you remember, is a value that you can write into the timer, and then you will generate you an interrupt, and it will wake you up so you can do a certain task. Now, you have 5 of these registers. What happens if you have 6 events that you have to schedule? How could you deal with that? You basically have to virtualize your timer, right? You somehow have to juggle and figure out, okay, event number 6 will be the event that comes the last. So I first handle my first one, and once that's handled, I will write event number 6 into that particular compare register. That way you could do it. So you have to have some sort of a linked list or a list that you keep in software that has a list between which event happens at what particular time. And this list has to be somewhat ordered in software. So that's exactly what virtual timers are. Virtual timers in software is a software implementation of your compare registers that needs only one compare register to have a potentially infinite amount of schedulable events that you can have. So how do they work? The simple idea is, let's say we have 10 events that we want to generate. So we make a linked list of these events. Every element in the linked list is ordered by time of their occurrence, and every event has a function handler that should be called at a certain particular time, right? So what we do is, we then in our timer take the first element out of the list, schedule a compare event for that event. When that event happens, we remove it from the list, look at the next event, schedule that one, etc., etc. And that's where you go through the list. Now, if somebody wants to add something into the list, they have to order it into that linked list, right? It has to go into the right time of the list so that you can actually schedule it later on. What are some of the problems? Well, it only works for compare timer use. Captures are really difficult to virtualize, but at least you can now schedule your events that way, as many as you want. Another problem is the interrupt service routine now will become slower. Because all of a sudden your ISR happens and then you have to go in software through a linked list, finding which element you have to deal with. That takes time and it's not instantaneous anymore. What else could happen during implementation? Well, you all of a sudden have a linked list that you have to share between your interrupt service routines and software code, right? When software tries to schedule something, it will have to add an element into the linked list. But as you remember from the interrupt lecture, what happens if an interrupt happens while you're adding something into the linked list? So you have to be very careful and use and disable interrupts while modifying these shared variables and these shared components. Same with deletion, right? Deletion happens inside the interrupt service routine. So if you try to add something and then he comes and deletes something out of it, you can get big mumble jumble with sharing these two elements. Yes?
You trigger, like intentionally trigger an interrupt from your
You can.
An interrupt that modifies the
But then you somehow have to tell the interrupt that this is actually not a timer interrupt, but actually an adding interrupt, right? And then you still have to somehow give data to that interrupt service routine, which might not be easy to do, right? It is easier to just turn off interrupts, yeah. Just disable interrupts, do your modifications, and re-enable them. And if an interrupt happens in between, well, it will be handled right after. Another problem, how do we deal with a modulo counter, right? This particular counter that we had here, assume it's 16-bit, so we can count up to 2 seconds. What if your event is 5 minutes from now? How do you schedule that? Any ideas?
Software bits.
Yes. Software bits. Remember, your timer will probably tell you when it overflows, right? Will generate an interrupt when it overflows. So you could just read that interrupt and then have a software bit counter that just counts how often did we overflow. And that way, you can actually extend your timers in software fairly easily. What else would be nice? Well, it would be nice if instead of just an event that happens once, we could tell, okay, this event should happen every 10 seconds, right? So that's another one of these features you can fairly easily implement in virtual timers by just having a mode together with in your linked list that will tell, well, schedule this event again in 10 seconds from when it happened last time. A one-shot event would be, well, you don't need to reschedule that when it happened now, but you could have very easily reoccurring events that way. That's actually a big issue. What happens if two events should happen at the exact same time in your software? Well, you now have to decide which one of them you want to do first and which one do second. Depending on these events, if they take a long time, it could be that your events now get out of sync, and that could become a problem. So virtual timers are really nice because oftentimes you don't have limits in how many events you can actually schedule in them. At the same time, they're not as precise anymore as a compare register itself. So oftentimes good for stuff that has soft delays and soft latencies. If you have to have something that's at a very precise time, it's really difficult to do in a software virtualized system. Data structure can be a little bit of an issue. You have to think about how to implement such a data structure. And yes, you will implement one of them in Lab 5 for your timers. You actually will write a virtualized, you will virtualize your timer itself. And this is a suggestion that you will get for this implementation. So what we have is a timer handler. So you have a function that has to be a timer handler itself. You initialize a function that initializes, of course, your hardware timer. You have a function that's called start timer one shot. And when you call this function, what happens is you give it a handler and a time when this handler should be called. You can do the similar thing with a start timer continuous where you have a handler and a delta t. So now this timer will be called every delta t times. And you probably also want a function that's a stop timer where if you have a continuous timer that counts all the time, you want to give it this particular handler and it should remove it from the linked list so you can actually stop this particular timer to not reoccur again. Some more implementation details. What you have to do is your initialization. Of course, you set up the hardware, you initialize the linked list, and you set the current timer to null because right now in the beginning initialization there is no timers. This data structure for one of the nodes can be something like this where you have a handler, you have a time associated with it, a certain mode, and a link to the next timer. That would happen. So now implementing these functions will be your job. Start timer one shot adds the handler into the linked list at the right time. So you have to traverse your linked list, find the right time where you have to add it in there. Start timer one continuous, you have to add it again correctly into your linked list. And if you stop the timer, you have to traverse your linked list and actually remove that particular element out of your linked list. In your interrupt service routine, something like this has to happen where you have first clear the interrupt and the pending bit, then you set timer to the current timer. So that's the timer that has to be expired right now. You look if this timer is a continuous mode. If it is, you re-add it back into your list, ordered of course. And then you go and treat the different interrupts down here with the right flags that you have to do. Yes?
Is this kind of like a priority queue implementation?
Kind of.
Or are we not even worried about priorities?
You could add a priority bit into it, yes. Where you say, like, if you have somebody else that comes at the exact same time, you can give them different priorities. You could totally do that.
We went through that whole section of interrupts that were given priorities.
Okay.
I was curious if that was translating into this.
No, not directly. No. I don't think so. Okay. Any questions to timers? Yes, before we wrap this up.
Each struct adds an interrupt, right?
No, there's only one interrupt that will happen all the time, right? Your interrupt is this interrupt service routine. That's your timer that will basically tell you, hey, we had a compare right now. And whenever this compare happened, you know that the top element in your linked list was the one that caused this element. So you will execute that particular event, remove it from the linked list, look at the next element, and set up your timer for that next element to happen. Any other questions? Was timers okay? Clear, mostly? Because software-wise, you will see it in Lab 5. You will implement a timer and actually use it in software a lot. So it will probably give you a lot more information on how timers work and in software itself. Okay, memory landscape. We saw this picture before, right, where we had different interfaces. And what we talked about was this particular bus interface here on the right-hand side. We talked about bus transactions, just a little reminder of them. We have read and write transactions. These devices will tell us how to use a particular memory chip. We talked about interfacing itself. We had address bits, we had data bits, chip-enabled bits, etc., etc. So now comes the big question. Well, what's inside this memory array here? Right? Okay, we know how we have addresses, we have data that we talk to, we have to twiddle a couple of bits properly so that data either comes out or gets put back into the memory. Now the big question is, what's in this particular memory? Because there are several different categories. The first one, read-only memory, or ROM, usually only able to read this memory. You cannot write back into it. The other one is a random access memory, or RAM. Now, technically, this is a historic term. ROM these days is also random access memory, but RAM is usually considered to be read and writable, and that's the two different categories, ROMs and RAMs. Now, we can have volatile memory. Volatile memory means that if you lose power, it's gone, it's volatile. Or non-volatile memory, where if power is gone, the memory actually stays and keeps its content. So next time you power on, you can actually read it back out again. So if you look at this in a little diagram, what we can have is RAM can be volatile or non-volatile. We have the different types of static RAM and dynamic RAM, which we'll look at. Non-volatile memory, EPROMs, flash memory, FRAM, MRAM, and BBS RAM. While as ROMs, well, there is no volatile ROM, usually. It's always non-volatile, and what we have is like mask ROMs, PROMs, or EPROMs. So how do you choose a memory for your different applications? Well, there are a lot of different objectives that you have to look at. Of course, volatility. Do you need the data when power is gone or not? Cost, how expensive is it? Organization, is it a 64K by 1 bit, or is it an 8K by 8 bit, or other architectures that can be there? Yes?
Is that a reference to alignment?
We will look into it. It's in how the architecture of your memory block is. Interface, is it serial, parallel, synchronous, or asynchronous? Access times, how fast is the memory that you need? That will oftentimes be determined by your application. If you have a high-speed video application that you have to write into memory somewhere, you have to make sure your memory is actually fast enough. Modify times, so sometimes the read times and modify times are different. Erase process, if you need to erase your data, how do you erase it? Is it a block erase, or do you have to expose it to UV light for 5 minutes? Granularity, do you erase a page, a word, a bit, or the whole chip, as in with the UV light? And the architectures can really vary quite a bit. However, most of the times, this is the very general architecture. That's why before you just saw a little block of memory array. What you have is you have a certain amount of word lines, you have memory cells in there, and then you have bit lines that come out. So whenever you select a certain word line, the bit lines will be set accordingly to what's stored in these particular memory cells. So the question now becomes, what should be the aspect ratio? Right? How many word lines do you have? How many bit lines do you have down here? The question also becomes now interesting because these memory cells are not zero size. So if you actually look at them, they have a certain size, and that particular size of these memory cells is first of all defined by the technology that's used to manufacture them. That's what we see here. So the technology over time, you're going down, 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 down in size, right, in our lambda. And that will actually define the physical size of our possible transistors that we can put into our memory cells. Over time, we were making better and better progress. So here, for example, for flash, NORAM, and FERAM. FERAM was fairly big, but it's coming down, down, down. And this is from 2004. So today, we actually have solutions to make them down here. We found solutions how to do it. And now you can see the difference. FERAM is a lot bigger than flash NORAM in physical size. So what could be some of the implications about that? What if the cell size is, for example, let's take this example here where we have about 0.1 micrometer squared versus about 5 micrometers squared. What's the implications of that? Longer distance, less memory density, right? If your memory cell is 5 times bigger, then you can have less memory on the same chip area. So if you have less memory on the same chip area, what does that mean?
Overall less memory.
Overall less memory and more expensive for the same amount of memory, right? Because now all of a sudden, if you want 1 megabit of FE RAM, the chip is a lot bigger, it's a lot more silicon, so the process becomes more expensive to actually make this particular memory.
Does it take more power to actually hold the larger chip?
Probably also more power, yes. Not necessarily, but it can be more power, yes. Okay, so let's look at physical on-chip memory configurations. Physical on-chip memory is typically squared because that has the best performance with aspect ratio. It minimizes the length of word line and bit lines and thus becomes more efficient inside of your chips. The shorter length means that we have shorter propagation times through the chips, right? The longer the wire is, the longer it takes to go through it, the faster the data access becomes, and the smaller the read cycle time. Now, let's do a little exercise. Let's assume we have a n-square memory cell configuration. Okay. How big is an n by n square array? If we assume we take 1 megabit of data, and let's say that we have a 10 micron per cell width. How big will this square be if it's an n by n, or if it's an n squared by 1? Right? So one of them would be is a 1 megabit, so it's 1,000 this time, 1,000 that time, right? N by n. And the other one would be really long, 1 by a million. Let's assume each cell is 10 micro. How big is this chip? An inch? How did you get from millimeters to inches? Okay. What is it? Each cell is 10 micrometers. Yes. How much this would be? 10,000 micrometers, right? How much is that? That's 10 millimeters? Yes. So 10 millimeters by 10 millimeters. What about this guy here? How long would be an array of 1 million cells at 10 micrometers? Yes? 10 meters. Clearly, this is not a chip you want to have in your embedded system, right? Okay, what's the transition time through this chip? Assume the speed of light on a chip is about 2/3 c. How long does it take to access the worst case in this chip and the worst case in this chip? So trying to access this last bit here, how long does it take? The last one, that's the worst case. Because in this guy here, you have to traverse 10 meters of chip to get to that last bit there. How long does it take to get 10 meters at 2/3 the speed of light? Sounds about right. Like something in the few nanoseconds of time. So, okay, let's put 2 and 2 together. Up there I say shorter length means shorter propagation time. He just calculated for a chip that's 10 meters long, the propagation time to just get to that bit would be in a few nanoseconds. Okay, 50 nanoseconds? No, it should be less. It is 50 nanoseconds? Okay, yes. Sounds about right. So if you remember, when we did this exercise on the access speed of this memory cell that we had, how much was the fastest one to guarantee our access? 90 nanoseconds, right, was the access time. Remember the 90 nanoseconds one that we had, that exercise we did? So okay, if it takes 50 nanoseconds to get to a bit at 10 meters, right, it takes almost no time in an actual squared, or even if this would be a little bit skewed kind of architecture. So no, propagation delay is not the big latency that you will have to deal with. So what else could it be? What else is there that we have to worry about? So it's not just the time it takes for a signal to go through your chip.
Signal iteration, you've got all that asynchronous logic,
Yeah. There's some logic in there. So there's some logic to select the different lines in here that will add delays in there. But also accessing your memory bit itself, right? Depending on what the technology of that particular bit is, it might take some time to tell you if it's a 1 or if it's a 0. That won't be an instantaneous answer out of it. So know that the propagation delay itself doesn't have much to do with the area or how the behavior of it is. It's more about the surrounding logic and the particular technology that you have in your memory cells that will determine the access time and the speed at which you can actually read that memory chip out. Okay, external memories. Well, external memories are most of the time tall and narrow. So internal, we have squared because it makes it more convenient for our chips themselves. If we have them external, we actually have them in a different architecture, tall and narrow. And the reason of this is because we can then change the amount of pins it needs to access this particular chip. Remember, we only have a limited amount of pins and I/O interfaces that we can interface with. So we want to reduce that particular amount. So let's assume we have a tall and narrow configuration. And let's say we have a 64 kilobit interface. So the 64K can have a lot of different architectures internally. It could be a 64K by 1, right? So we would have 16 addresses and 1 data bit. That would be only 17 pins. That would be really nice, right? You can access 64K of data with just 17 pins. We can also do a 32 by 2. So now you have 15 addresses and 2 data lines. Also pretty good still. All right, let's go to 16 by 4. So now you have 16K 4-bit addresses, 18 pins. All of a sudden we have 4 bits that we get out at once, but we need now 18 pins to interface to it. It becomes worse and worse. 8K by 8, all of a sudden we need 21 pins. Or if we go to a 4K by 16, we now all of a sudden have 28 pins. Or if we go one further, if you want to actually a full 32-bit data interface, a 2K by 32K, we all of a sudden need 34 pins. So basically, if you think about it, every address bit that you add can double the amount of memory that you can address, right? While with the data bits, you can't do that. So that's why you want a tall and narrow interface, like a 64K by 1. Well, you probably don't want a 64K by 1 because a 1-bit interface would be very painful to read out. But you probably want to go something with like a 8 or a 16-bit data interface. Because else it just becomes untractable with the amount of data pins that you will need on your microcontroller to interface with these chips. Any questions? Yes?
What about serial communication?
Serial communication? There you are, of course, on your own. Like, so basically what happens is that the controller now inside the chip will do the whole decoding and encoding. You will have a lot fewer pins, of course, to use, sometimes as few as 2 pins that you only need, like for an I2C, for example. At the same time, it's a lot slower than one of these configurations, right? Because here, for example, with a configuration of 8K by 8, with one read, you get 8 data bits out. With a serial communication, you have to serialize the whole interface. It will be a lot slower than what you can do with these parallel interfaces. Okay, let's look at a couple of internals. We have seen this before, where you have the address bits, we have a decoder, and the muxer down here. We have the logic of output enable, chip select, and write enable, and we have some input and output buffers that can push out the data bit or actually read the data bit back in. Quick exercise for you guys. Assume, right here we have now a 4x4 interface, right? So we have 4 word lines, and we have 4 data lines that get muxed down. What happens if we would go from a 4x4 array to a 16 by 1 array? How would the interface change? What would the decoder look like? What would your demuxer look like? We only want 1 data bit out. What would this guy be here? 4 in? 0 in? So 16 by 4 is a 16. 16 by 1 would be 16 word lines, 1 data line. Is it? It's a good question. Is it XY or is it YX?
Rows by columns. That's how they do it in math. I don't know about as engineers, we might have to go
Okay.
against the math.
Well, in that case, okay, then let's do a 1 in, 16 out. No, you don't need more data lines. You just have a mux down here. So how would this mux look like? 16?
4 select lines, 6 select lines.
Exactly. So this would be 1 tall, 16 long. You have 16 outputs, and down here you have a 16 to 1 mux that would select the bit out of this particular memory array. The other way around, the 16 to 1 would be on this side here, and you would select which particular word line would get selected. That would throw out the particular bit down here. Okay. I'm going to jump over this one because we're running out of time a little bit. And let's actually talk about non-volatile memories. The easiest non-volatile memory is mask ROM. Mask ROM is very expensive to manufacture the very first time. Because what you basically have to do is you have to manufacture a mask with which you will make a physical chip. But once you have this mask, that's usually a manufacturing cost of about $200,000, the silicon you use later on is a lot cheaper. So once you have the mask, making the chips themselves is really cheap. So if you have to make a lot of them, mask ROM is what you want to go with. How does it work? Well, it physically burns and makes the connections in your silicon, and they will not be able to change later on. So in this particular case, this will give you an example where they use diodes to connect word lines to data lines. In this case, we have an 8 by so you said 3 by 8. Would this be then? Is that right? Enoch, what did you say? Rows before columns?
Rows by columns.
Okay, so it would be a 3 by 8.
Rows, K is columns.
And what happens is that you have 3 data bits input, which will select one of the word lines, and then you get a result down here on the bit lines. So what's the output for a data 101? 101. Is this one here? So we have a connection, connection, connection. Can somebody read this diagram and tell me what the output would be? 111. Why? It's correct.
It is, well, just because it's coming off of those
lines to the diode to connect the.
Correct. So the diode basically connects here, right? So if this word line is high, so this connects here, so this will be high, this will be high, this will be high, so we get a 1, 1, 1. So let's take 1, 1, 0. It would be word line number 6. So this is connected. Again, this is a 1. This is a 1. So what happens to this line here? It's not connected. Why is it a 0 though? Pull down resistor, exactly. Now here we have a resistor. So that will pull this line down to 0. So we have a 1, 0, 1. Mask run. Fairly simple to do. Next, EEPROM. These are erasable, programmable, read-only memories. So these are memories that you cannot write back into, but you can erase them. And you can erase them by exposing them to UV light. If you have ever taken apart an old computer, you have seen probably some chips in them that had like a little sticker on top of each of them. And if you took the sticker out, what you saw is something like this. You had like a glass and an exposed chip underneath it. That's an EEPROM. How you delete them is you take that sticker away, put them into a machine like this down here, and you erase them by exposing it to UV light for 5 minutes, and then they are all erased. And in this particular case, erasing means you write ones into each and every location. And programming them means that you write some of them back to 0. Once you have done that, you cannot change this data again, unless you re-erase the whole chip by exposing it to UV light. EEPROMs are rarely seen anymore, and because they're expensive to manufacture, because this chip has to have a quartz on top of it, so it's possible to expose it to UV light, but that's very expensive to make, and so we basically don't see them anymore. What's used these days is mostly flash memory, right? Probably pretty much everyone is running around with a USB stick in their pockets. That's flash memory. So how does flash memory work? It's electrically erasable memory, so you can erase it with an electric write into them. The erase size is a block, so it's actually not a word, so you cannot erase byte by byte or 16-bit by or 32-bit. It's usually a whole block that you have to erase at once. Erase circuitry, instead of having it inside the memory cell, it's pulled out into the logic, and that's why you can only erase a whole block at once. But by doing this, you take the logic, and instead of having it duplicated in each and every memory cell, you have it outside. It makes the whole chip cheaper. That's why flash memory these days is getting cheaper and cheaper and cheaper to manufacture. You can write bits into memory cells. So once you erased a block, that actually makes it from 0 to 1s. You can erase parts of it or write into it by writing some of these bits to 0. Once you have the data written into it, if you want to erase it, you have to erase the whole block before you can actually start writing over it again. The technology is what's called a floating gate technology, and unfortunately, you can only have about 10 to 100K of erases. So flash memory is not a very good memory if you have to use it to write and read from it all the time. So if you have USB sticks, better make backups because they're prone to break eventually, especially if you run, for example, Libero on top of it or use it as a live file system to read and write from it all the time. And they do break eventually. And once they're broken, well, your data is gone if you don't have a backup. Any questions to non-volatile memory? No? Okay, then let's talk about volatile memory. What's volatile memory? Well, pretty much all your RAM that you have in your computers is what's called volatile memory. There are two main technologies. One of them is static RAM, the other one is dynamic RAM. This is a static RAM technology. Static means that once you write into it, as long as you keep power on it, the data will stay in there. You don't have to do anything with it. There are two different things that you can do with them. One of them would be a 4T configuration. The other one is 6T configuration. This back here is the 6T configuration, where you have access lines on the left and right, and you configure the PFETs in the configuration in there such that when you write something in it and you let go, this is a stable system. It either will output a 1 or a 0. It has extreme fast access times, so it's on the orders of nanoseconds, But because you need 6 transistors to make them, its physical size is fairly large compared to what's called dynamic RAM or DRAM. DRAM has 1 transistor and 1 capacitor. So what happens is, to write into it, you either charge the capacitor to represent a 1, or you discharge the capacitor to represent a 0. Now, what's the problem with a capacitor? They leak. They discharge themselves. So what you have to do with DRAM is you have to occasionally refresh the status on it if you don't use memory cells. So you have a refresh cycle. In addition to that, what happens if you read the capacitor out?
Erase it.
You erase it. So once you read a DRAM memory cell, you actually have to write it back if you want to keep the data in there. So access time is not as fast as static memory. At the same time, because we only have a capacitor and a FET, the size is very small, so you can make a lot of them inside of a very small area of die. So it's a lot cheaper, but it costs more in order to use it later on with refreshing it or reading and writing out of it. And that's what all of this is just in text.